June 17, 1943, Wright Field, Dayton, Ohio. Colonel Fred Dent stood beside a wooden structure so massive that the hangar doors had to be completely removed to allow it to be towed outside. At 105 feet long with a wingspan of 150 feet, the Waco CG-4A glider dwarfed everything around it except the purpose-built experimental glider before him, the XCG-16, capable of carrying a fully operational M22 Locust light tank into combat. "This changes everything we understand about airborne warfare," Dent said to the assembled engineers and military observers. "If we can deliver armor directly onto the battlefield by air, we eliminate the greatest weakness of airborne forces. No longer will paratroopers land armed only with small weapons and hope relief arrives before enemy armor overwhelms them." Through the morning mist, the experimental glider sat on the tarmac, its enormous cargo doors open, revealing the tank secured within. The M22 Locust inside weighed 7.4 tons, fully loaded with fuel and ammunition. The glider that would carry it weighed another 8,700 pounds empty. Together with the tow cable and crew, the combination approached 10 tons that would have to be lifted into the air, flown across hostile territory, and landed on improvised strips behind enemy lines. What Colonel Dent and the observers could not fully anticipate was how this ambitious program would push engineering to its absolute limits, reveal fundamental contradictions in airborne doctrine, and ultimately produce aircraft that, while technically successful, arrived too late and in circumstances too changed to fulfill their intended mission. The story of tank-carrying gliders represents one of World War II's most ambitious and least known technical achievements. A program that solved seemingly impossible problems only to discover that the problems themselves had become obsolete. This is not a story of failure. The engineers succeeded brilliantly at what they were asked to do. The pilots who flew these massive gliders demonstrated extraordinary skill. The concept was sound, the execution competent, and the results impressive. But the story illustrates a fundamental truth about military technology. By the time revolutionary systems become operational, warfare itself may have evolved in directions that make those systems irrelevant. Today we will examine every aspect of the tank glider program. We will explore the engineering challenges of building aircraft capable of carrying armored vehicles. We will document the development of specialized tanks light enough to be air-portable yet effective enough to matter in combat. We will follow the pilots who trained to fly these ungainly giants. We will analyze the tactical doctrine that envisioned how tank gliders would be employed. And we will understand why, despite technical success, tank gliders made almost no impact on World War II combat operations. This is the story of ambition meeting physics, of vision confronting reality, and of brilliant engineering applied to solving problems that battlefield conditions had already rendered moot. This is the story of the experimental gliders that delivered tanks into battle. To understand why the Allies invested enormous resources into developing tank-carrying gliders, we must first understand the fundamental tactical problem that airborne forces faced in World War II. Paratroopers and glider infantry could be inserted deep behind enemy lines, seizing critical objectives before ground forces arrived. But they landed with limited heavy weapons and no armor, making them vulnerable to enemy counterattacks, particularly by armored units. The German invasion of Crete in May 1941 demonstrated both the potential and the peril of large-scale airborne operations. German paratroopers captured the island despite heavy casualties, but they faced disaster when British armor counterattacked. German airborne forces had no effective anti-tank weapons beyond small arms and a few anti-tank rifles. If British commanders had employed their armored forces more aggressively, the German paratroopers might have been destroyed. The lesson was clear. Airborne forces needed their own armor to survive against mechanized counterattacks and to provide the mobile firepower necessary for rapid exploitation. But conventional tanks were far too heavy to be transported by air. The M4 Sherman tank, standard American medium tank, weighed 30 tons. The British Churchill infantry tank weighed 40 tons. Even light tanks like the M3 Stuart weighed 12.5 tons, well beyond the capacity of any transport aircraft or glider in service in 1941. The solution required approaching the problem from both directions simultaneously. First, develop aircraft capable of carrying significant loads. Second, develop tanks light enough to be carried by those aircraft while still being militarily useful. Both challenges involved fundamental engineering trade-offs between weight, strength, capability, and cost. The American airborne warfare doctrine that emerged in 1942 envisioned large-scale glider operations, delivering entire units with their equipment directly onto objectives. Unlike paratroopers, who were scattered across drop zones and required time to assemble and organize, glider troops would land in formed units, immediately ready for action. Gliders could carry heavy equipment that could not be parachuted, including jeeps, artillery, ammunition, and potentially armored vehicles. The British, who pioneered military glider development, focused initially on troop-carrying gliders like the Airspeed Horsa and the massive general aircraft Hamilcar. The Hamilcar deserves particular attention because it represented the first serious attempt to create a glider capable of carrying armored vehicles. With a wingspan of 110 feet and a cargo capacity of 17,500 pounds, the Hamilcar could carry a Tetrarch light tank weighing approximately 7.5 tons. The Tetrarch was specifically designed for airborne operations, though that was not its original purpose. Designed in 1937 as a fast reconnaissance tank, the Tetrarch was lightly armored, armed with a 2-pounder gun, and weighed 7.5 tons. When the British began developing airborne armor concepts in 1941, the Tetrarch's light weight made it the only tank that could potentially be carried by air. British engineers modified it slightly for airborne service, but fundamentally it remained a pre-war design adapted to a new role. The Hamilcar glider program demonstrated that carrying tanks by air was technically feasible. The glider could be loaded through a hinged nose that opened upward, allowing the tank to drive directly into the cargo compartment. Once loaded, the nose closed and locked, and the entire assembly could be towed by a Halifax bomber. After landing, the nose opened again and the tank drove out, theoretically ready for immediate action. Theoretically deserves emphasis. The Hamilcar's first operational use came during Operation Tonga, the British airborne component of D-Day. 6 Hamilcars carrying Tetrarch tanks participated and the results were mixed. Several landed successfully, and their tanks were able to engage German forces. Others crashed or were damaged during landing, rendering the tanks unusable. One Hamilcar broke apart completely during towing, killing everyone aboard. The Americans observed the Hamilcar program with great interest. If the British could deliver 7.5-ton tanks by glider, surely American engineering and industrial capacity could develop systems to deliver even more capable armored vehicles. This confidence, combined with the expanding American airborne program, led to formal requirements for American tank gliders in early 1942. The U.S. Army Airborne Command, established in March 1942 under Major General William C. Lee, had responsibility for developing airborne doctrine, training airborne units, and defining equipment requirements. General Lee understood that airborne forces needed organic armor to be fully effective. His staff developed detailed requirements for a tank that could be delivered by glider, engage enemy armor and fortifications, and support infantry operations until link up with ground forces. The requirements were extraordinarily demanding. The tank had to weigh no more than 7.5 tons to be compatible with planned glider capacity. It had to be armed well enough to engage enemy light tanks and fortifications. It had to have sufficient armor to resist small arms and shell fragments. It had to be mechanically reliable because maintenance support would be limited in airborne operations. And it had to be capable of being driven directly off the glider and into combat without extensive preparation. Simultaneously, the glider requirements were equally challenging. The aircraft had to carry 7.5 to 8 tons of cargo, including the tank, fuel, ammunition, and crew. It had to be towable by existing aircraft like the C-46 or C-47. It had to land on improvised strips without requiring paved runways. It had to allow the tank to be loaded and unloaded quickly. And it had to be manufactured cheaply enough to be expendable, since gliders were generally expected to be abandoned after their first mission. These requirements contained inherent contradictions that would plague both programs. A tank light enough to be carried by air would necessarily have thin armor and limited armament. A glider large enough to carry a tank would be enormous, difficult to tow, and challenging to land safely. The entire concept assumed that airborne operations would occur in circumstances where the advantages of tank delivery outweighed these limitations. In early 1942, when these programs began, such circumstances seemed plausible. The Allies were planning large-scale airborne operations to support the invasion of Europe. Intelligence suggested German airborne forces were developing similar capabilities. The race to develop tank gliders appeared to be a critical aspect of the broader competition to dominate airborne warfare. In March 1941, before the United States entered World War II, the U.S. Army Ordnance Department issued a requirement for a light tank weighing no more than 9 tons that could be transported by air. The weight limit was somewhat arbitrary, based on rough estimates of what might be achievable with future transport aircraft. No one seriously expected such a tank to be operational soon. Then Pearl Harbor occurred, America entered the war, and the airborne tank requirement suddenly gained urgency. The Ordnance Department refined the specifications and issued contracts to 2 manufacturers, Marmon Harrington and the J. Walter Christie Company. Both companies had experience designing light armored vehicles, though neither had built anything quite like what the Army now wanted. The specifications demanded a vehicle weighing no more than 7.5 tons fully loaded, armed with a 37mm gun and coaxial machine gun, armored against small arms fire, capable of 35 miles per hour on roads, and mechanically simple enough to be maintained under field conditions. The crew would be 3, driver, gunner, and commander, who also served as loader. Marmon Harrington, an Indianapolis-based manufacturer that had built light tanks for export before the war, approached the problem systematically. Their engineers understood that meeting the weight limit would require ruthless elimination of everything unnecessary. Every component would be scrutinized, every system simplified, every possible ounce removed. The hull and turret would be welded aluminum armor, lighter than steel but adequate for the thin armor thicknesses that the weight limit imposed. The armor would be 25mm thick at maximum on the frontal surfaces. The sides and rear would have only 12 to 15mm, barely enough to resist heavy machine gun fire. This armor would not protect against any anti-tank weapon, but the tank's role envisioned operating in rear areas where anti-tank weapons might be less common. The 37mm M6 gun, chosen as the main armament, was already obsolete by 1942 standards. American M3 Stuart light tanks carried the same weapon, and combat experience in North Africa was demonstrating that 37mm guns were marginally effective against German armor, even in 1941. By the time an airborne light tank entered service, the 37mm would be hopelessly outmatched by German armor developments. The Ordnance Department understood this limitation but accepted it as inevitable. A more powerful gun would require a larger, heavier turret and more internal space for ammunition storage. The 37mm was the best that could be accommodated within the weight limit. The tank would carry 50 rounds of 37mm ammunition and 2,500 rounds for the coaxial .30 caliber machine gun, enough for a day of combat operations if ammunition was conserved. The engine selection proved critical. Marmon Harrington chose the Lycoming 0435T, a 6-cylinder horizontally opposed gasoline engine producing 162 horsepower. This engine was derived from aircraft engines, chosen for its high power-to-weight ratio. At approximately 400 pounds, it provided adequate power while not consuming too much of the precious weight budget. The transmission was a Borg-Warner unit with 5 forward gears and 1 reverse. The suspension used torsion bars, which were lighter than the vertical volute spring suspension used on most American tanks. The tracks were narrow, only 11.5 inches wide, and made of rubber-bushed steel links to reduce weight and noise. The prototype was designated the T9 and weighed 6.7 tons in initial tests. Trials at Aberdeen Proving Ground in Maryland revealed numerous problems. The armor was too thin to be welded reliably with existing techniques. The engine overheated during extended operation. The transmission was unreliable. The suspension was too soft, causing excessive pitching over rough terrain. The gun mounting had insufficient traverse and elevation range. Engineers redesigned components through 1942. The armor was changed to welded steel, which was heavier but more reliable. The engine cooling system was improved. The transmission was strengthened. The suspension was stiffened. Each improvement added weight. By the time the T9E1 revised prototype was tested in early 1943, it weighed 7.2 tons, still within the specification but with minimal margin remaining. The tank received the designation M22 in September 1943 and entered production at Marmon Harrington's facilities. The company was not a large-scale manufacturer like General Motors or Ford, which built thousands of Sherman tanks. Marmon Harrington's production capacity was limited, suitable for specialized vehicles but not for mass production of standard tanks. The initial production contract called for 1,900 M22 tanks to be delivered by mid-1944. This number reflected the ambitious plans for airborne operations that existed in 1943. The Airborne Command envisioned multiple airborne divisions, each potentially including a battalion of airborne tanks. 1,900 tanks would equip these units with initial vehicles plus training tanks and attrition reserves. Reality intervened rapidly. Production problems, design changes, and shifting priorities delayed deliveries. The first production M22 was not completed until April 1943, later than planned. Quality control issues caused several tanks to be rejected. The company's limited capacity meant production ramped up slowly. More significantly, operational requirements were changing. By late 1943, Allied planners were recognizing that large-scale glider operations faced enormous challenges. The glider fleet was never as large as originally envisioned. Losses during training and operations consumed gliders faster than they could be replaced. And the tactical circumstances where tank gliders would be valuable seemed less common than anticipated. The M22 production contract was reduced first to 830 tanks, then to 830 with an option for more if needed. Ultimately, only 830 M22 tanks were manufactured, before production ended in February 1944. Of these, APPROX IM-ATELY 260 were delivered to the British under Lend-Lease, where they were designated the Locust, the name by which the tank is generally known today. The M22 Locust that emerged from this development process was a compromised vehicle, as any tank designed to such restrictive weight limits inevitably would be. It was fast, reliable when properly maintained, and mechanically simple. The crew appreciated its compact size and ease of operation. But it was appallingly vulnerable to any anti-tank weapon, inadequately armed for engaging enemy armor, and limited in cross-country mobility by its narrow tracks and light weight. Tactically, the Locust was envisioned operating in roles where its limitations would matter less. It would land behind enemy lines where heavy anti-tank weapons might be absent. It would engage infantry, fortifications, and light vehicles rather than enemy tanks. It would provide mobile firepower and psychological impact until link-up with ground forces brought heavier armor forward. In these circumstances, the Locust might be adequate despite its obvious weaknesses. Whether such circumstances would actually occur on the battlefield remained to be seen. But first, the gliders to carry the Locust had to be developed, tested, and produced in sufficient numbers to make airborne tank operations possible. The Waco Aircraft Company of Troy, Ohio, emerged as the primary American manufacturer of military gliders during World War II. Waco had been building civilian gliders and light aircraft since the 1920s, and had extensive experience with fabric-covered tubular structures and wooden construction techniques. When the Army Air Forces issued requirements for military gliders in 1941, Waco was positioned to respond quickly. The company's CG-4A, designated the Hadrian by the British, became the standard American troop and cargo glider. Over 13,900 CG-4A gliders were built by Waco and 15 other manufacturers during the war, making it the most widely produced American military glider. The CG-4A carried 13 troops, or approximately 3,750 pounds of cargo, towed by a C-47 or similar aircraft, and landed on primitive strips using simple skids rather than wheeled landing gear. But the CG-4A could not carry a tank. Its cargo compartment was too small and its structural capacity too limited. A specialized tank glider would require a complete redesign, essentially creating a new aircraft while incorporating lessons learned from CG-4A operations. The Waco engineering team, led by Chief Engineer Ralph Haviland, began work on what would become the CG-13 in early 1942. The basic configuration was determined by the fundamental requirement: carry an M22 tank weighing up to 7.5 tons plus crew and minimum fuel. The cargo compartment had to be at least 15 feet long, 7 feet wide, and 6 feet high to accommodate the tank. The floor had to be strong enough to support the concentrated weight of the tank's tracks without collapsing. The resulting aircraft was enormous by glider standards. The fuselage measured 60 feet long, with a cargo compartment occupying approximately 20 feet of that length. The wing spanned 85 feet, larger than a CG-4A, but still short of what would be needed for the later, more ambitious designs. The empty weight was projected at 6,700 pounds, meaning the loaded glider with tank would weigh approximately 22,000 pounds. This weight created immediate towing problems. The C-47 standard tow plane for the CG-4A was rated to tow approximately 7,000 pounds. A loaded CG-13 would exceed this by a factor of 3. The only aircraft with sufficient power were large bombers like the B-17 or B-24, but using strategic bombers as glider tugs was operationally impractical and wasteful of scarce resources. The C-46 Commando, a larger transport aircraft entering service in 1943, offered more promise. With twin 2,000 horsepower engines, the C-46 could theoretically tow heavier loads than the C-47, but even the C-46 would be operating near its limits towing a loaded CG-13, and the combination would have marginal performance and limited range. The structural design of the CG-13 pushed the boundaries of wooden aircraft construction. The wing used a wooden box spar with plywood covering, reinforced with fabric in non-critical areas to save weight. The fuselage was constructed from welded steel tubing in the cargo area, where maximum strength was required, transitioning to wooden formers and stringers covered with fabric toward the tail. The cargo loading system deserved particular attention. The nose section was designed to swing upward on massive hinges, opening the entire front of the aircraft. The tank would be driven up a ramp directly into the cargo compartments, secured with chains and tie-downs, then the nose would be closed and locked. After landing, the process would reverse, with the nose opening and the tank driving out and immediately into action. This loading system was mechanically simple but required precision manufacturing. The nose hinges had to be enormously strong yet not too heavy. The latching mechanisms had to hold the nose closed against aerodynamic loads during towing and gliding. Seals had to prevent too much air leakage that would create drag and control problems. The first CG-13 prototype was completed in March 1943 and underwent ground tests at Wright Field. Engineers loaded it with ballast equivalent to an M22 tank and conducted structural tests, towing tests, and systems evaluation. The structure proved adequate, with no failures or excessive deflections under load. The nose opening mechanism worked as designed. The control systems provided adequate response, though pilots reported that the glider felt sluggish and heavy, as would be expected from such a large aircraft. Flight testing began in April 1943 with a C-46 as tug. The combination proved marginal in performance. The C-46 could tow the loaded glider but required long takeoff runs and climb slowly. Range was limited because the C-46's engines consumed enormous quantities of fuel hauling the glider. The conclusion was that the CG-13 was technically feasible but operationally problematic. While the CG-13 program proceeded, Waco was also developing an even more ambitious design, the CG-4A modified to carry a Locust tank. This might seem impossible given that the CG-4A was designed for 3,750 pounds and the tank weighed 15,000 pounds. But engineers proposed a radical modification that would essentially create a new glider using some CG-4A components. The CG-4AM, as this variant was designated, would use the CG-4A's wing and tail surfaces but incorporate a completely redesigned fuselage. The cargo compartment would be enlarged and strengthened. The nose would be redesigned for tank loading. The landing gear would be reinforced to handle the increased weight on landing. The advantage of this approach was that CG-4A wings and tails were already in production at multiple factories. Creating a new fuselage design was easier than designing an entirely new aircraft. If the CG-4AM worked, it could potentially be produced quickly by modifying existing production lines. Several CG-4AM prototypes were built and tested in late 1943. The results were disappointing. The modified glider was heavier than anticipated and flew poorly. The CG-4A wing, while adequate for a 7,500-pound glider, was marginal for a 22,000-pound aircraft. Landing characteristics were dangerous, with high sink rates and a tendency to nose over if the brakes were applied too aggressively. Most critically, the CG-4AM could not be towed by a C-47, requiring the same C-46 tug as the CG-13, since it offered no advantages over the CG-13 and had worse flight characteristics. The CG-4AM program was cancelled after the prototype phase. Meanwhile, the CG-13 program continued with production contracts issued in late 1943. Waco was to build 100 CG-13 gliders at its Troy, Ohio facility. Ford Motor Company would build another 200 at its Kingsford, Michigan plant, which had been converted to glider production. Northwestern Aeronautical Corporation would manufacture additional units in St. Paul, Minnesota. These production contracts reflected the optimistic planning of 1943, when large-scale airborne operations still seemed central to Allied strategy. If each of the planned American airborne divisions received a company of tank gliders, and if operational losses were high as expected, hundreds of gliders would be needed. The production plan seemed reasonable given the anticipated requirements. But by early 1944, the requirements were changing rapidly. Operational experience with gliders was demonstrating that losses were even higher than expected. Training accidents, combat losses, and abandoned gliders after single missions consumed gliders at alarming rates. The industrial capacity to build gliders was less than anticipated, with wood shortages, labor issues, and quality control problems limiting production. More fundamentally, tactical doctrine was evolving. Large-scale glider operations, while still planned, were being recognized as extremely difficult and risky. Concentrating hundreds of slow, defenseless gliders in single airstreams created enormous air traffic control challenges. Landing areas had to be carefully selected and prepared. Enemy anti-aircraft fire could devastate glider formations. The circumstances where tank gliders would be valuable seemed increasingly rare. The CG-13 production program was scaled back before the first production gliders were completed. The Ford contract was reduced from 200 to 88 gliders. The Northwestern contract was reduced proportionally. Ultimately, only 132 CG-13 gliders were completed before production ended in 1944. The CG-13s that were produced went into service with airborne units for training. Pilots practiced towing, landing, and tank loading procedures. Infantry units practiced coordinating with airborne armor. The gliders proved adequate for their intended purpose, though the limitations were obvious to everyone involved. But a new requirement was emerging that would push glider design to its absolute limits. If the Allies were going to invade Japan, as planning in 1944 assumed, airborne operations would be essential. The terrain in Japan and the Pacific Islands favored airborne insertions. And those operations would need armor support. Not just the 7.5-ton Locusts, but potentially heavier vehicles. This requirement would lead to the most ambitious glider program of World War II, the XCG-16 and XCG-20, designed to carry loads approaching 10 tons. In early 1944, as planning for the invasion of Japan intensified, the U.S. Army Air Forces issued a requirement for a glider capable of carrying either an M22 Locust tank or a M24 Chaffee light tank. The M24 was entering production as the replacement for the obsolete M3 Stuart, incorporating lessons learned from combat in North Africa and Europe. It weighed approximately 18 tons fully loaded, more than twice the weight of the Locust. Carrying an 18-ton tank by glider seemed almost impossible using existing technology. No tug aircraft could lift such weight. The glider itself would have to be massive, with wings spanning well over 100 feet, and structural members capable of handling loads that approached the limits of wooden construction. Yet the requirement was issued, and manufacturers were invited to submit proposals. Chase Aircraft Company of Trenton, New Jersey, responded with the most ambitious design. Michael Straukoff, Chase's chief engineer and a Russian émigré with extensive experience in heavy aircraft design, proposed a glider with a 110-foot wingspan, a cargo compartment large enough for a Chaffee tank, and a loaded weight approaching 40,000 pounds. The design was designated the XCG-20, but recognizing that the XCG-20 might be too ambitious for immediate development, Chase also proposed a smaller variant optimized for the Locust tank. This aircraft, designated the XCG-16, would have an 85-foot wingspan, carry 10 tons of payload, and be towable by a C-46 or C-54. It represented a compromise between capability and practicality. The Army Air Forces awarded contracts for both designs in March 1944, though with the understanding that the XCG-16 would receive priority. If the XCG-16 proved successful, the XCG-20 program would continue. If the XCG-16 encountered insurmountable problems, both programs might be cancelled. Strakov's team began detailed design work immediately. The fundamental challenge was structural: how to build a wooden aircraft capable of handling the loads imposed by carrying and landing with 10 tons of cargo. Wood is an excellent structural material for its weight, but it has limits. The wing spars would have to be massive, the fuselage frames enormously strong, and the attachment points for the tow cable capable of sustaining forces approaching the entire weight of the loaded aircraft. The wing design used a multi-spar configuration rather than the single-spar layout common in smaller aircraft. 3 parallel spars ran the length of each wing, with the main spar in the center carrying the primary loads and the forward and aft spars providing torsional, rigidity and distributing loads from the wing's fabric covering. The spars were laminated from multiple layers of Sitka spruce, a wood selected for its high strength-to-weight ratio and availability. Each spar was over 12 inches deep at the wing root, tapering to 8 inches at the tip. The laminations were glued under pressure using waterproof adhesives, then machined to precise dimensions. The quality control requirements were stringent because any defect in a main spar could cause catastrophic structural failure during towing or landing. The fuselage structure used a hybrid approach. The cargo compartment, which would contain the tank, was built around a steel tube framework welded together in a jig to maintain precise alignment. This steel structure could handle the concentrated loads from the tank's tracks without the risk of crushing wooden members. Outside the cargo area, the fuselage transitioned to wooden construction to save weight. The cargo loading system followed the established pattern of an upward opening nose section. But given the size of the XCG-16, the nose assembly was enormous, measuring approximately 12 feet tall when opened. The hinges used automotive-type bearings rather than simple pins, providing smoother operation and reducing wear. Hydraulic struts assisted in opening and closing the nose, reducing the manual effort required. The landing gear deserved particular attention because landing a 40,000-pound glider imposed enormous stresses on the gear components. The XCG-16 used a tricycle configuration with a nose wheel and 2 main gear legs. Each main gear leg had dual wheels to distribute the load. The gear was designed to be semi-retractable, reducing drag during flight, but not fully retracting to save weight and complexity. The shock absorption system used a combination of rubber donuts and oleo-pneumatic struts. The rubber donuts provided initial cushioning during touchdown, compressing to absorb energy. The oleo struts, containing both oil and compressed air, provided damping to prevent the glider from bouncing after landing. The entire landing gear system weighed over 1,500 pounds, a significant portion of the glider's empty weight, but essential for safe operations. The control system was conventional for gliders of this era, using cables and pulleys to connect the control stick and rudder pedals to the control surfaces. But the control surfaces themselves were massive, with the rudder standing over 20 feet tall and the elevators spanning 30 feet. Moving these surfaces required significant force, particularly at the high speeds encountered during towing. To reduce control forces, the engineers incorporated aerodynamic balance panels ahead of the hinge lines. These panels moved in the opposite direction to the control surface itself, generating forces that partially offset the hinge moments. The result was that even at high speeds, a single pilot could fly the glider without excessive fatigue. The cockpit was designed for a crew of 2, pilot and co-pilot. Both had full flight controls, allowing either to fly the glider. Instrumentation was minimal by powered aircraft standards, consisting of an airspeed indicator, altimeter, bank indicator, and compass. Glider pilots navigated primarily by visual references and communicated with the tug aircraft through an intercom system connected by wires running along the tow cable. The tow cable itself was a specialized component, manufactured from braided steel wire with a breaking strength of over 40,000 pounds. The cable was typically 350 feet long, allowing the glider to fly in the relatively smooth air behind and slightly below the tug aircraft's propeller wash. Shorter cables caused the glider to be buffeted by turbulence, while longer cables made control more difficult and increased the risk of the cable snagging obstacles during takeoff or landing. Construction of the first XCG-16 prototype began at Chase's Trenton facility in May 1944. The work proceeded methodically as craftsmen laminated spars, assembled frames, and fitted components together. Quality inspectors examined every glue joint, every bolt, every structural member. The prototype was not just an experimental aircraft, but a proof of concept for what might become a production glider if the design proved successful. The empty glider weighed 8,700 pounds when completed in August 1944, slightly more than the design target but still acceptable given the structural margins built into the design. Ground tests verified that all systems functioned correctly, that the cargo loading mechanism worked smoothly, and that the structure could sustain the expected loads without excessive deflection. The first flight test occurred on September 15, 1944, at Clinton County Air Force Base in Wilmington, Ohio. A C-54 Skymaster, one of the most powerful transport aircraft available, served as the tug. The glider carried ballast equivalent to an M22 tank, bringing the total weight to approximately 17,500 pounds, about 80% of the expected maximum weight. The takeoff required over a mile of runway as the C-54 slowly accelerated, dragging the massive glider behind it. Once airborne, the combination climbed to 5,000 feet for basic handling tests. The pilot, Lieutenant Colonel Paul Hazen, reported that the glider flew smoothly and responded well to control inputs, though it felt heavy compared to the CG-4A gliders he was familiar with. After 45 minutes aloft, Hazen released the tow cable and flew the glider in a gradual descent toward the landing strip. The glide ratio was approximately 15:1, meaning from 5,000 feet altitude, the glider could glide approximately 15 miles horizontally. This was adequate for selecting landing sites after release, but not exceptional by glider standards. The landing was uneventful, with the glider touching down at approximately 65 miles per hour and rolling to a stop within 1,500 feet. The landing gear absorbed the impact without damage. Post-flight inspection revealed no structural problems, no failures of any systems, and no damage that would prevent immediate reuse. Subsequent test flights explored the full performance envelope. The glider was loaded to maximum weight with an actual M22 tank aboard. The C-54 required nearly all available runway to take off with this load, barely becoming airborne before reaching the end of the pavement. Once airborne, the climb rate was minimal, approximately 200 feet per minute, and the C-54's engines operated at maximum continuous power for the entire climb to altitude. Range tests revealed significant limitations. The C-54 consumed fuel at nearly double its normal rate when towing the loaded glider. The maximum range for the combination was approximately 200 miles, compared to over 2,000 miles for the C-54 operating independently. This limited range would constrain operational planning, requiring glider operations to be launched from bases close to the objective area. The landing characteristics with maximum weight concerned some test pilots. The touchdown speed increased to nearly 75 miles per hour, and the landing roll extended to over 2,000 feet even with maximum braking. Landing on unprepared fields in combat conditions would be challenging and dangerous. The glider required relatively smooth ground and adequate length, conditions that might not exist at forward airfields or improvised strips behind enemy lines. Despite these limitations, the XCG-16 was declared successful. It had demonstrated that a 10-ton payload could be carried by glider and that the tank could be loaded and unloaded efficiently. The Army Air Forces approved production of 64 XCG-16 gliders under the designation CG-16A, with deliveries scheduled to begin in early 1945. But even as production preparations began, the strategic situation was changing in ways that would make the entire program irrelevant. While engineers worked on developing tank gliders and airborne tanks, tactical planners grappled with the question of how these systems would actually be employed in combat. The doctrine that emerged revealed both creative thinking about airborne warfare and fundamental misunderstandings about battlefield realities. The basic concept was straightforward. Airborne forces would be inserted by parachute and glider to seize critical objectives behind enemy lines. The tank gliders would land shortly after the initial insertion, providing armored support before enemy reinforcements could arrive. The tanks would help defend the captured objectives against counterattacks, provide mobile firepower for expanding the perimeter, and serve as psychological weapons that would demoralize enemy forces who had not expected to face armor. The planning staff at the Airborne Command developed detailed procedures for tank glider operations. The gliders would be released at altitudes between 2,000 and 5,000 feet, approximately 5 to 10 miles from the landing zone. Pilots would navigate to the landing zone using visual references, descending gradually to touch down on prepared strips or suitable fields. Ground personnel would secure the landing area, assist with offloading the tanks, and provide immediate support. The tanks would be combat-ready immediately upon landing. Crews would be aboard during the flight, strapped into their positions inside the tank. Upon landing, the glider's nose would open, the tank would start its engine, and drive directly out and into action. The entire process, from touchdown to tank operational, was expected to take less than 5 minutes. This procedure required extraordinary coordination and precise execution. The landing zone had to be large enough to accommodate multiple gliders landing simultaneously or in rapid succession. The terrain had to be suitable for both glider landings and tank operations. Enemy anti-aircraft defenses had to be suppressed or destroyed before the gliders arrived, and friendly forces had to be positioned to provide immediate support to the landed tanks. The tactical employment scenarios envisioned several specific missions for airborne tanks. The first and most critical was defense against enemy armor counterattacks. Intelligence assessments suggested that German forces would respond to airborne landings with rapid mechanized counterattacks, potentially including tanks. The M22 Locust, while inferior to German tanks in direct combat, could engage enemy armor from concealed positions, using its mobility to avoid decisive engagement while inflicting damage. The second mission was providing mobile fire support for infantry operations. The 37mm gun, though ineffective against armor, was adequate for destroying buildings, bunkers, machine gun nests, and other fortifications. The tank's machine gun provided suppressive fire, and the tank itself served as a mobile command post and rallying point for infantry units. The third mission was exploiting breakthroughs and pursuing retreating enemy forces. Once the initial objectives were secured and ground forces linked up with the airborne units, the tanks could spearhead further advances, maintaining pressure on disorganized enemy forces. The doctrine specified that tank glider units would be organized as separate companies attached to airborne divisions. Each company would have 17 M22 tanks, 4 platoons of 4 tanks each plus a company headquarters tank. Supporting this company would require 17 CG-13 or CG-16 gliders, 17 tug aircraft, ground support personnel, mechanics, ammunition handlers, and all the other elements necessary for sustained operations. The logistics of deploying even a single tank glider company were formidable. Each tank required approximately 150 gallons of fuel for several days of operations. Ammunition loads included 50 rounds of 37mm and 2,500 rounds of .30 caliber. Spare parts, tools, and maintenance supplies had to be carried. All of this had to be either loaded aboard the gliders or delivered by subsequent supply missions. The doctrine emphasized that tank glider operations required favorable conditions to succeed. Clear weather was essential for glider navigation and landing. Adequate intelligence on landing zones was critical to avoid landing in unsuitable terrain. Air superiority over the objective area was mandatory to prevent enemy fighters from attacking the defenseless gliders. And the overall tactical situation had to favor rapid exploitation before enemy reinforcements arrived in strength. Training exercises tested these procedures and revealed numerous problems. At Fort Bragg, North Carolina, where the Airborne Command conducted most of its training, tank glider companies practiced loading, towing, landing, and tactical operations repeatedly. The exercises demonstrated that the procedures could work under ideal conditions with trained, motivated personnel and adequate support. But the exercises also revealed how fragile the entire system was. Weather delays disrupted carefully planned schedules. Mechanical problems with gliders, tugs, or tanks caused mission failures. Landing zone selection proved more critical than anticipated, with even slight variations in terrain causing difficulties. Coordination between air and ground elements required extensive practice and was prone to breakdown under stress. One particularly revealing exercise occurred in March 1944, involving the simulated insertion of a tank glider company in support of an airborne division attacking a notional objective. Of the 17 gliders launched, 14 reached the landing zone, 2 turned back with mechanical problems, and 1 crash-landed short of the objective after the tow cable broke. Of the 14 that reached the landing zone, 12 landed successfully. 1 hit trees on approach and was destroyed, and 1 landed hard enough to damage its landing gear and immobilize the tank. Of the 12 tanks that landed successfully and drove off their gliders, 11 reached their assigned positions and participated in the exercise. One broke down with engine problems shortly after leaving the landing zone. The exercise was considered reasonably successful, achieving an approximately 65% effectiveness rate, but participants recognized that combat conditions would be far less forgiving than training exercises. The psychological aspects of tank glider operations received particular attention in planning. Glider pilots were already flying one of the most dangerous missions in military aviation, riding unarmed, defenseless aircraft into hostile territory with no option for escape if things went wrong. Adding the weight and size of tank gliders increased the danger substantially. Larger gliders were more difficult to control, required longer landing rolls, increasing the risk of ground accidents, and presented bigger targets for enemy fire. Tank crews faced their own psychological challenges. Riding inside a tank during glider flight was an unnerving experience. The crew was strapped into their positions, unable to see outside, sensing every movement and bounce of the glider through the tank's suspension. If the glider crashed, the crew might be trapped inside the tank. The potential for fire was ever present, as aviation fuel, ammunition, and the tank's own fuel created multiple ignition sources. The training program addressed these concerns through graduated exposure. Crews started with ground training, becoming familiar with glider procedures without flying. Then they flew in passenger gliders to experience the sensations of glider flight. Next they rode in tank gliders with ballast instead of tanks, then finally with actual tanks. By the time crews participated in full exercises, they had dozens of hours of glider time and understood what to expect. Despite these preparations, the psychological strain remained significant. Post-exercise interviews revealed that many crew members found glider operations more stressful than conventional tank combat. The lack of control, the dependence on the glider pilot and tug aircraft crew, and the vulnerability during flight created anxiety that affected performance. The British, who had their own tank glider program using Hamilcar gliders and Tetrarch tanks, developed parallel doctrine with similar conclusions. Their experience in Operation Tonga during D-Day provided the only significant combat use of tank gliders in the European theater, offering valuable lessons about what worked and what did not. 6 Hamilcars carrying Tetrarchs participated in the initial British airborne assault. Of these, 4 landed successfully and their tanks were able to engage German forces, providing valuable support to lightly armed paratroopers. 2 Hamilcars suffered problems during towing or landing that rendered their tanks unusable. This 67% success rate was consistent with American training experience, suggesting that even under optimal conditions, 1/3 of tank gliders might be lost or damaged. The combat value of the 4 operational Tetrarchs was significant but limited. They engaged German infantry positions, destroyed several machine gun nests, and provided mobile firepower that helped secure initial objectives. But when German armor arrived, the Tetrarchs were outmatched and had to avoid direct engagement. 2 of the 4 tanks were eventually destroyed by German fire, and the other 2 were abandoned when they broke down mechanically. This experience suggested that tank gliders could contribute to airborne operations but would not fundamentally alter the tactical balance. They provided a capability that did not otherwise exist, but that capability had strict limits. Against well-equipped enemy forces with armor and anti-tank weapons, airborne tanks would struggle to survive. Their optimal employment required careful selection of objectives where their unique advantages could be exploited. As 1944 progressed and planning for the invasion of Japan began, American planners revisited the tank glider concept with these lessons in mind. They concluded that tank gliders might be particularly valuable in the Pacific theater, where Japanese forces often lacked heavy anti-tank weapons and where terrain favored airborne operations. The decision to proceed with production of the CG-16A reflected this strategic assessment. But events were about to overtake planning once again, rendering these elaborate preparations obsolete. While the XCG-16 program demonstrated that a 10-ton payload glider was feasible, the XCG-20 represented an attempt to push glider technology to its absolute limits. The requirement to carry an M22 Chaffee light tank weighing 18 tons demanded an aircraft unprecedented in size and structural capability for a non-powered aircraft. Chase Aircraft's design team, led by Michael Straukoff, Approach the XCG-20 as an exercise in scaling up proven concepts rather than introducing revolutionary new technologies. The aircraft would use the same materials, construction methods, and design principles as the XCG-16, just larger and stronger. This conservative approach reduced development risk but guaranteed the aircraft would be enormous. The final XCG-20 design featured a wingspan of 110 feet, 10 feet longer than the Hamilcar, and among the largest wings ever designed for a wooden aircraft. The fuselage stretched 69 feet from nose to tail, with a cargo compartment 25 feet long, 8 feet wide, and 7 feet high. The empty weight was projected at 18,000 pounds. Fully loaded with an M22 tank, crew, fuel, and ammunition, the total weight would approach 54,000 pounds, over 27 tons. No single tug aircraft in the American inventory could tow this weight. Even the B-29 Superfortress, the largest and most powerful American bomber, would struggle. The solution proposed by Chase was tandem towing, two C-54 or C-46 aircraft flying in formation, each connected to the glider by separate tow cables. The glider pilot would coordinate with both tug pilots through intercom systems, maintaining position behind and between the two tugs. This tandem towing concept had been tested experimentally with smaller gliders and proven theoretically feasible. Each tug would pull approximately half the glider's weight, bringing the load on each aircraft into manageable ranges. The challenge was coordination. The two tugs had to maintain precise formation throughout the flight, matching speeds, altitudes, and climb rates. If one tug encountered engine problems or other difficulties, both tugs had to respond identically or risk imposing asymmetric loads on the glider that could cause structural failure or loss of control. The wing design pushed wooden aircraft construction technology to its limits. The main spar at the wing root was over 18 inches deep, laminated from dozens of layers of spruce glued together under pressure. The spar tapered to 10 inches at the tips, still enormous by normal aircraft standards. Supporting this primary structure were two secondary spars and numerous ribs creating the wing's aerodynamic shape. The wing loading, the weight per square foot of wing area, was substantially higher than on the XCG-16 or any other operational glider. This high wing loading improved cruise efficiency but meant higher landing speeds and longer landing rolls. The calculated touchdown speed exceeded 85 miles per hour, and the landing roll would extend beyond 3,000 feet even on smooth, level ground. The landing gear was correspondingly massive. Each main gear leg used 4 wheels in a tandem configuration, with each wheel rated for 10,000 pounds load. Heavy-duty shock absorbers incorporated both rubber and oleo-pneumatic elements. The entire landing gear system weighed over 2,500 pounds, nearly 14% of the glider's empty weight. The control surfaces were so large that conventional manual controls would have been physically impossible for pilots to operate. The XCG-20 incorporated aerodynamic balance panels and servo tabs that amplified pilot inputs, allowing reasonable control forces. Even so, flying the XCG-20 would require significant physical strength, particularly during landing, when control responses had to be both precise and forceful. Construction of the first XCG-20 prototype began at Chase's expanded Trenton facility in July 1944. The company had been awarded a contract for 1 prototype plus a structural test article that would be used for ground testing to verify the design's structural integrity. If the prototype flew successfully, production contracts might follow. The construction process was methodical and time-consuming. The massive wing spars required weeks to laminate, cure, and machine. The fuselage frames had to be assembled in fixtures, ensuring precise alignment. The cargo compartment's steel tube structure had to be welded carefully to avoid introducing stresses that could cause cracks or failures. By November 1944, the structural test article was complete and undergoing ground tests. Engineers applied loads equivalent to the expected flight loads plus safety margins, measuring deflections and strains throughout the structure. The test article withstood these loads without failure, though some areas showed higher stresses than anticipated and required reinforcement in the flight prototype. The flying prototype was completed in February 1945, over 3 months behind the original schedule. Delays resulted from material shortages, particularly the high-grade spruce required for the spars, and quality control issues that required rework of some components. The completed glider weighed 18,400 pounds empty, slightly more than the design target but still acceptable. Ground tests revealed some concerns. The glider felt large and unwieldy during taxiing tests. The control responses seemed slower than desired, and there was lingering uncertainty about whether the tandem towing concept would work reliably with an aircraft this large and heavy. The first flight test was scheduled for March 15, 1945, at Clinton County Air Force Base. 2 C-54 transports would serve as tugs, with an experienced test pilot crew aboard each. The glider would be piloted by Lieutenant Colonel Paul Hazen, who had flown the XCG-16 first flight, along with Major Robert Wilson as co-pilot. The glider would carry ballast equivalent to about 60% of an M22 tank's weight, reducing risk during the initial flight while still testing the aircraft under substantial load. The morning of March 15th was clear with light winds, ideal conditions for a test flight. The 2 C-54s taxied into position ahead of the massive glider, their tow cables connecting to reinforced attachment points on the glider's nose. The ground crew verified that all connections were secure, that the glider's controls moved freely, and that communication systems between all three aircraft were functioning. The takeoff roll began with both C-54s advancing throttles in coordination. The glider began moving, accelerating slowly behind the tugs. At approximately 75 miles per hour, the glider's wheels lifted from the runway, becoming airborne before the tugs. This was expected because the glider's wing generated lift at lower speeds than the heavily loaded C-54s. Hazen held the glider in a slight climbing attitude, careful not to rise too high above the tugs and impose excessive upward force on the tow cables. The C-54s rotated at 90 miles per hour and became airborne, climbing gradually. The combination took nearly 2 miles of runway to become fully airborne and clear obstacles at the end of the field. Once safely airborne, the formation climbed to 5,000 feet at approximately 300 feet per minute, a labored climb reflecting the enormous combined drag of 2 transports and a massive glider. At altitude, Hazen conducted basic handling tests, exploring how the glider responded to control inputs, how it flew in turns, and how stable it was in different configurations. The glider handled adequately, though not exceptionally. Control responses were slower than the XCG-16, and the glider required constant attention to maintain coordinated flight. The tandem towing arrangement worked but demanded precise flying by all three crews. After 40 minutes aloft, Hazen prepared for landing. He coordinated with the tug pilots, and both C-54s reduced power while descending toward the release altitude of 2,000 feet. At precisely 2,000 feet, Hazen pulled the cable release handle, and the glider separated from both tugs simultaneously. Flying free, the XCG-20 descended in a gradual glide toward the landing zone. The glide ratio was approximately 12-1, somewhat worse than the XCG-16 due to the higher wing loading. Hazen adjusted the glider's path to line up with the runway, making small corrections to compensate for wind drift. The final approach was flown at 90 miles per hour, maintaining enough speed for good control response but not so much that the landing roll would be excessive. At 10 feet altitude, Hazen began the flare, raising the nose to reduce descent rate. The glider settled onto the runway at approximately 85 miles per hour, the landing gear absorbing the impact with a pronounced but not severe bounce. The landing roll exceeded 3,500 feet, using most of the available runway. Even with maximum braking and the tail skid digging into the pavement, the glider's momentum carried it forward for a considerable distance. Hazen brought the glider to a complete stop with several hundred feet of runway remaining and taxied clear of the landing area. Post-flight inspection revealed no structural damage, no failures of any systems, and no problems that would prevent immediate reuse. The XCG-20 had successfully flown, demonstrating that even a 27-ton loaded glider was technically feasible. The test program would continue with additional flights exploring the full performance envelope and eventual testing with an actual M22 tank aboard. But even as the test program proceeded, the strategic context that had driven the XCG-20's development was evaporating. The war in Europe was entering its final weeks. German resistance was collapsing. The need for tank gliders in European operations had passed, if it had ever truly existed outside planning documents. In the Pacific, the strategic situation was evolving rapidly. The capture of Iwo Jima and Okinawa provided bases for the planned invasion of Japan. but the invasion planning was being overtaken by other developments. The atomic bomb program, unknown to most military planners, was approaching completion. Strategic bombing of Japan was intensifying, and the Soviet Union's entry into the Pacific War was being negotiated. The tank glider program continued through spring and early summer 1945, but with decreasing urgency and shrinking budgets. The end of the war in Europe in May allowed resources to be redirected to the Pacific, but it also prompted fundamental reconsideration of invasion plans. The casualties suffered at Iwo Jima and Okinawa suggested that invading Japan would be enormously costly, strengthening arguments for alternatives to invasion. When Japan surrendered on August 15, 1945, following the atomic bombings and Soviet declaration of war, the tank glider program lost its remaining justification. The XCG-20 would never carry an M24 tank in combat. The CG-16A production program was terminated with only a handful of gliders completed. The M22 Locust tanks in storage would never see the large-scale airborne operations they were designed for. Despite years of development, extensive training, and significant investment of resources, tank gliders saw combat only once during World War II, and even that single use was limited and almost accidental. Operation Varsity, the airborne component of the Rhine crossing in March 1945, included a small number of British Hamilcar gliders carrying Tetrarch tanks. The operation provided the only realistic test of whether tank gliders could contribute meaningfully to combat operations. Operation Varsity was planned as the largest single-day airborne operation of the war, surpassing even the D-Day airborne assaults in the number of troops delivered simultaneously. The U.S. 17th Airborne Division and British 6th Airborne Division would be dropped and landed east of the Rhine River, seizing key terrain and disrupting German defenses to facilitate the river crossing by ground forces. The British 6th Airborne Division included the 6th Air Landing Brigade, which had organic armor in the form of the 6th Airborne Armored Reconnaissance Regiment. This regiment was equipped with Tetrarch light tanks, designed to be carried by Hamilcar gliders. For Operation Varsity, 8 Hamilcar gliders would carry Tetrarchs, providing the airborne force with armored support from the initial moments of the landing. The planning for the tank glider element emphasized several lessons learned from previous operations and training. The gliders would land in the initial wave, not in follow-up missions, ensuring the tanks would be available immediately. The landing zones were carefully selected for adequate size and suitable ground conditions. Air superiority would be absolute, with overwhelming fighter escort preventing German aircraft from interfering. And the ground tactical situation was expected to be favorable, with German forces weakened by months of combat and Allied ground forces crossing the Rhine simultaneously. The morning of March 24, 1945, was clear with good visibility, ideal conditions for a massive airborne operation. The air armada that launched toward the Rhine included over 1,500 transport aircraft and 1,300 gliders, carrying nearly 17,000 troops plus their equipment. 8 Hamilcar gliders, each carrying a Tetrarch tank, were part of this vast formation. The tow aircraft for the Hamilcars were Halifax bombers, operating near the limits of their towing capacity. Each Halifax-Hamilcar combination required careful coordination during the flight across the Rhine. The formations maintained strict radio silence to avoid alerting German defenses, communicating through pre-arranged visual signals. German anti-aircraft fire began as the formations crossed the Rhine, intensifying as they approached the landing zones. The transport aircraft and gliders flew through clouds of flak, with some aircraft taking hits and crews making emergency landings or bailouts. The Hamilcars, large and slow, were particularly vulnerable targets. One Hamilcar was hit by anti-aircraft fire during the approach, suffering damage to its control surfaces. The pilot struggled to maintain control but managed to reach the landing zone before the glider became uncontrollable. The landing was hard, collapsing the landing gear and damaging the Tetrarch inside. The tank could not be extracted and was abandoned. Another Hamilcar encountered a different problem. The tow cable parted prematurely, miles short of the release point. The glider pilot attempted to stretch the glide to reach the landing zone but fell short, landing in a field well away from friendly forces. The crew immediately started the Tetrarch and attempted to drive toward the landing zone, but German fire disabled the tank before it could link up with airborne forces. The remaining 6 Hamilcars successfully reached the landing zone and landed without catastrophic incidents, though several suffered damage from rough landings. The Tetrarchs were unloaded and immediately pressed into action. The crews had been briefed on expected German positions and tactical objectives, allowing them to begin operations without delay. The Tetrarch's first engagements involved suppressing German infantry positions that were firing on the landing zones. The 2-pounder guns, while ineffective against German armor, were adequate for destroying machine gun nests and fortified positions. The psychological impact of tanks appearing in the airborne bridgehead was significant, with German troops retreating from positions they might have held against infantry alone. As the morning progressed, the 6 operational Tetrarchs supported the consolidation of the airborne perimeter. They engaged German counterattacks, provided mobile firepower for infantry advances, and served as rallying points for British paratroopers organizing defensive positions. The tank commanders maintained radio contact with brigade headquarters, coordinating their movements with the overall tactical plan. By mid-afternoon, Allied ground forces crossing the Rhine had linked up with the airborne forces. Heavier armor, including Churchill tanks and Cromwell cruiser tanks, advanced into the bridgehead, relegating the Tetrarchs to secondary roles. Several Tetrarchs were damaged by German fire during the day's fighting. Others suffered mechanical breakdowns from the strain of continuous operations. By evening, only 3 Tetrarchs remained operational, and these were withdrawn to rear areas for maintenance. The post-operation assessment of the tank glider element concluded that the Tetrarchs had contributed positively but not decisively to Operation Varsity's success. They provided a capability that would not otherwise have existed in the initial hours of the operation, when airborne forces were most vulnerable. But their impact was limited by their small numbers, light armament, and vulnerability to German anti-tank weapons. The British 6th Airborne Division's after-action report noted that the tank gliders suffered a 25% loss rate during the delivery phase, higher than the overall glider loss rate of approximately 15%. This suggested that tank gliders were more vulnerable than ordinary gliders, possibly due to their larger size, slower speed, and limited maneuverability. The report also noted that the Tetrarch's combat effectiveness was constrained by their obsolete armament and thin armor. While useful against infantry and fortifications, they could not engage German armor on equal terms. The report recommended that future airborne tank operations should employ vehicles with more capable armament, while acknowledging the fundamental weight constraints that made this difficult. American observers studying Operation Varsity reached similar conclusions. The XCG-16 and CG-16A gliders under development could deliver M22 Locusts with similar capabilities to the Tetrarch, suggesting American tank glider operations would face similar limitations. The XCG-20's ability to carry the more capable M24 Chaffee might partially address these concerns, but the XCG-20 remained experimental and its operational characteristics uncertain. More fundamentally, observers questioned whether the complexity and resource demands of tank glider operations justified their limited contribution. Each tank glider required a specialized aircraft, a powerful tug, a trained glider pilot, and extensive support infrastructure. In Operation Varsity, 8 tank gliders delivered 6 operational tanks that fought effectively for several hours, before being superseded by heavier armor arriving by conventional means. Could those same resources have been better employed in other ways? 8 tug aircraft could have towed 16 standard gliders, delivering perhaps 200 additional infantrymen or their equivalent weight in ammunition, anti-tank weapons, or other supplies. Would this have contributed more to the operation's success than 6 light tanks? These questions had no definitive answers, but they highlighted the fundamental cost-benefit analysis that military planners must conduct when allocating scarce resources. Tank gliders represented sophisticated solutions to specific tactical problems, but the cost and complexity of those solutions had to be justified by proportionate military advantage. The end of World War II in August 1945 terminated most military development programs that had not yet reached operational status. The tank glider program was among the casualties. Production of the CG-16A was halted with only 64 gliders completed. The XCG-20 program was cancelled with only the single prototype ever flying. The M22 Locust tanks in storage were declared surplus, with most eventually scrapped or sold to foreign governments. The British, who had employed tank gliders in combat, conducted more thorough post-war analysis than the Americans. The Royal Air Force and British Army collaborated on a comprehensive study of airborne operations, including extensive examination of tank glider employment. The study's conclusions were sobering for advocates of airborne armor. The study confirmed that tank gliders could technically deliver armor to airborne forces, as demonstrated in Operation Varsity and earlier operations. But the study questioned whether this capability justified the resources required. Each tank glider demanded a large, expensive aircraft and a powerful tug, resources that might be better employed in other roles. The tanks delivered were lightly armed and armored, effective only against limited opposition. The study recommended that future British airborne forces should focus on anti-tank weapons that could be delivered by conventional gliders or parachute, rather than attempting to deliver actual tanks. Recoilless rifles, portable anti-tank missiles, and similar weapons could provide anti-armor capability without the complexity and resource demands of tank gliders. The Americans conducted similar analyses, reaching generally similar conclusions. The U.S. Army's Airborne Board at Fort Bragg published a report in 1946 examining all aspects of airborne operations during World War II. The section on airborne armor acknowledged the theoretical advantages of tank gliders, but noted the practical limitations revealed in training and the single combat employment. The report recommended that airborne divisions should be equipped with air-portable anti-tank weapons rather than light tanks. The development of recoilless rifles, particularly the 75mm M20 recoilless rifle entering service in 1945, provided infantry units with genuine anti-armor capability in a package weighing only 114 pounds. A single standard glider could carry multiple recoilless rifles with ammunition, providing more distributed anti-tank capability than a single light tank. The M22 Locust tanks that had been produced found limited post-war employment. Approximately 260 had been transferred to Britain under Lend-Lease during the war, and most of these remained in British service into the late 1940s. The British used them primarily for training, as the Tetrarchs were being retired and needed replacement vehicles for their airborne armored units. Some M22s were sold to Egypt in the late 1940s, where they saw limited service before being replaced by more modern British and American tanks. A few were retained by the U.S. Army for training and evaluation purposes into the 1950s, but by 1960, virtually all M22s had been scrapped or placed in museums. Their brief and limited service life concluded. The gliders themselves faced similar fates. Most CG-4A, CG-13, and CG-16A gliders were declared surplus immediately after the war. Some were sold as scrap with the wood being burned for fuel and metal components salvaged. Others were sold to civilian operators, who converted them for cargo hauling or destroyed them after finding no economically viable uses. A few gliders were retained for experimental purposes. The U.S. Air Force, newly independent from the Army in 1947, conducted some experiments with transport gliders through the early 1950s, exploring whether gliders might have roles in tactical airlift. The experiments confirmed that powered aircraft were superior for virtually all military transport missions, and the glider experiments were terminated. The XC-G20 prototype remained at Wright Field after the war, used occasionally for research into heavy load carrying. In 1950, Chase Aircraft converted it to powered configuration by installing two radial engines, creating the MS-8 Tetrarch. This powered version served as the basis for the C-123 Provider transport aircraft, which had a successful career through the Vietnam War era. But the connection to the original tank glider mission was tenuous at best. The lessons learned from the tank glider program extended beyond the specific technical achievements. The program illustrated several broader principles about military technology development that remain relevant decades later. First, technical success does not guarantee operational relevance. The engineers who designed tank gliders succeeded brilliantly at solving the problems they were given. They created aircraft that could carry tanks, that could be towed by available tugs, and that could land on improvised strips. But these technical achievements occurred in a strategic context that was evolving rapidly. And by the time the systems were ready, the problems they solved were less pressing than they had seemed during early planning. Second, military requirements must be continuously re-evaluated against changing battlefield conditions. The tank glider requirement made sense in 1942, When large-scale airborne operations seemed inevitable and airborne forces desperately needed anti-armor capability. By 1945, airborne doctrine had evolved. Alternative solutions like recoilless rifles had emerged, and the strategic situation had changed. The requirement should have been cancelled or modified earlier, saving resources that could have been applied to more pressing needs. Third, complexity imposes costs beyond simple resource expenditure. Tank glider operations required specialized aircraft, powerful tugs, trained pilots, ground support equipment, and elaborate coordination procedures. This complexity created numerous failure points and demanded resources that might have been better employed in simpler systems with broader applicability. Fourth, the perfect can be the enemy of the good enough. The drive to develop gliders capable of carrying ever heavier tanks led to increasingly ambitious designs like the XCG-20, which pushed technology to its limits without necessarily providing proportionate military advantage. More modest capabilities delivered sooner might have been more valuable than optimal capabilities arriving after the need had passed. These lessons influenced post-war military aviation development, though sometimes only after painful relearning. The helicopter emerged in the 1950s as the solution to many problems that gliders and parachutes had addressed imperfectly. Helicopters could deliver troops and light vehicles to precise locations, land and take off from confined areas, and extract forces after missions were complete. The Vietnam War would demonstrate both the capabilities and the limitations of helicopter-delivered armor, with similar debates about whether light armored vehicles justified their resource demands. The tank glider story also contributed to broader understanding of airborne warfare's evolving role. The massive airborne operations of World War II represented the peak of glider-based airborne operations. Post-war developments, including helicopters, improved parachute systems, and air-portable light vehicles, gradually made gliders obsolete. The last operational military gliders were retired in the 1960s, ending an era that had lasted barely 2 decades. Today, military forces face similar challenges in delivering armored vehicles to remote locations. Modern solutions include air-portable light tanks like the M8 armored gun system, designed to be carried by C-130 transport aircraft, and light armored vehicles that can be parachuted or internally carried by helicopters. These systems reflect lessons learned from World War II tank gliders. Keep vehicles as light as possible, design them for air transport from the beginning, and ensure they provide capabilities that justify their cost and complexity. Museums around the world preserve a handful of M22 Locust tanks and various military gliders, tangible reminders of this ambitious but ultimately marginal program. These artifacts allow modern observers to appreciate the engineering achievements involved while understanding why the systems never achieved the impact their developers hoped for. The National Museum of the U.S. Air Force at Wright-Patterson Air Force Base displays a CG-4A glider, the experimental gliders that delivered tanks into battle.